Oh, let me turn that off. Maybe that'll help. There's gotta be a way to turn the sound off. I don't know. Or how about mute?
Mute? Keyboard clicks will make it stop making noises when you type. That's
okay, good. What's that?
Oh, that's the setting you want. Unless you have other stuff.
Oh, okay.
Yeah.
Okay. I think we can get started. So hopefully, people can hear me and you can see the screen. So today, basically, we're just going to keep pushing through with Haskell, and I'm going to show a little bit at the terminal as we go here, and then I'll kind of switch back and forth. I'll probably just show a few things, and then I think I'll switch back just to writing because it gets a little bit easier. I don't know. We'll see. It's a little bit hard to write legibly with both of them going, but I'll do my best here. So before I get started, are there any questions? Okay. If you do have questions, please feel free to unmute, ask questions as we're going. So again, we're just going to keep plowing through Haskell stuff, and then homework 8 is out, and that's due in a week from today. And basically, there's a couple questions just to kind of like get you started using GHCI, the interpreter. And then the rest of it is for you to write functions, just some simple functions, just to get a feel for like writing functions in Haskell and using some of the things we talked about last time, as well as a couple things we'll talk about today. All right, so the first thing I just wanted to talk about quickly is just to kind of go, we need to have just a little bit better working understanding of types. So basically it's just like types revisited, but maybe a little bit more detail. So the basic types, which we've already seen in Haskell, are char. And this just represents a single character. And then bool, which we've seen, which just has two values, true or false. And then there's a primitive, a couple primitive types for integers. So the first is int. And this is basically a signed fixed width integer value. And it's either going to be 32 bits or 64 bits, just kind of depending on the architecture. There's a number of other like unsigned types, and there's explicit like 32-bit versus 64-bit types. So int is just kind of the basic int type. And then there's something called integer. And this is not a fixed width type. So an integer is basically like unbounded in size. Obviously it does have a bound, but it's for storing like big integers. Okay, and then there's a number of floating point basic types. The main one is double. And this is kind of like the default type, the floating point type in Haskell. So this is a 64-bit double precision floating point number, just like what you would find in like C, C++, Java. And again, this is kind of like just the default kind of hardware supported type for representing floating point values. So most of the time, if you're going to be working with floating point values, you're going to be using doubles. Okay, so we already kind of know about that for the most part. And then, so the next thing that is what you kind of have you need to have a little bit better understanding of or idea of are type classes. And we've kind of talked about this here and there. So if I start, whoops, I don't know what that is. If I start up GHCI, then when I ask for the type of a number like 42, it returns that 42 has the type, this weird thing. So in this case, it says 42 has the type, and then num A. And so the basic idea of, so I want to describe these a little bit more, just to give you a better sense for what this is saying. So first of all, what's going on here is that the A, this is really the type of the number 42. So this is what's called a type variable. And we know it's a type variable because it's a lowercase letter. So lowercase a, when we're talking about types, signifies that this is something that, this is a type variable. So every other, like concrete type, you'll notice in Haskell always starts with an uppercase letter. So both the basic types and the type classes, so in this example, num is a type class, these always start, all types start with an uppercase letter. So here, the A, which is lowercase, signifies that so lowercase a signifies that it's a type variable. Okay. So the way to sort of think about this is that 42 has any type A. Again, A is a variable that ranges over types, such that A is an instance of the num class. Okay, so we need to figure out what is the num type class? What does that even mean? And that's, we're going to kind of go through a few examples and describe this in a little bit more detail. So the first thing is a type class. Basically, all the type classes, the way I like to think of them are like interfaces in Java. So if you're familiar with Java, or if you're not familiar with Java, an interface is basically kind of like a class, but it's not. It's really a purely abstract class in the sense that you define class methods, but there's no implementations for the methods. So an interface only consists of a set of function declarations or function prototypes. There's no implementations for those functions. And so a type class is very similar to that. Basically, a type class just defines a set of functions. It's kind of like an interface. In Java, or a pure abstract class in C++. So if to be a member or to be an instance of the type class, you have to implement all of the functions in the type class. So for example, int is a member of the num type class, and as a concrete type, it basically has implementations for all the functions that num defines. Okay, so to be a member, whoops. Of the type class, whoops. I said members of the type class implement, sorry, the writing, all of the type class functions. So I think the one thing that people get hung up on when we talk about type classes is they hear the word class and they think C++ class or Java class. And it's really not the same as a class. It's really the same as like an interface. The other big difference is, so like in C++ or Java, if you have a class, you can create instances of a class, and we call those an object. So it's like a piece of data. Whereas in Haskell, a member of a type class is not an object, it's itself a type. And it basically just says it conforms to that type class, or it implements the functions of the type class. Okay, so I'm just going to walk through some examples of the kind of common type classes we're going to see. And you should have a good sense of what these are. So you have to kind of understand what they are in order to make much progress in Haskell with respect to types. Okay, so the first one is kind of one of the most basic type classes, which is called EQ. Basically what these do is they support equality testing. And so what I'm going to show you is basically how to find out information about a type class, and then you'll just kind of see what a type class is. So if I come over to GHCI, I can ask for information about things I can ask for information about whatever I'm interested in here. So I'm going to ask for information about this EQ type class. And it shows a ton of stuff. Okay, so but I'm going to go back up to the very top. Okay, so if we look at the top where it says class EQ, what this is basically giving us is the definition of the EQ type class. So what this line says is that A is a type variable. So A is a type that's a member of the EQ class if it supports equal, that function, and if it supports not equal, those two functions. So equal and not equal make up the EQ type class. Those are the functions you have to implement if you define it, if you want your type to be a member of the EQ type class. Are there any questions about that? And for now, we can not, so basically what comes after the colon, that's a function type. So we'll talk about that in a minute. You don't have to understand that as much as just this idea that there are certain functions that are tied to a type class.
So does that kind of mean that instead of objects, things can be thought of more as like types?
I don't know what that means exactly.
Well, like earlier when you said like you create an instance of something of like that becomes like an object.
Oh, I gotcha. Yeah. So it's like there's another. So there are objects, something like objects. They're actually called values. Okay, so you have values which are like objects, and then you have classes or you have types. So for example, so false is a value, and its type is bool, and bool belongs to different type classes. So there's like one level of instantiation above a type, which is a type class. So another way to say this is at the top level you have type classes. An instance of a type class is a type, and then an instance of a type is a value. And actually, so if we look at the EQ type class again on the left, what's after these two function definitions are like just a list of like all the things that are all the types that are members of the type class. So if we come down here, we can see that int is an instance or a member of the EQ type class. In other words, we can call equal on integers. Okay, so int is an instance of EQ, and then like the number 42, that's an instance or value of an int. Does that make sense?
Yeah, thank you.
So again, another example would be bool. So bool is a member or is an instance of the EQ type class. So I can check, does false equal false, or does false not equal true? Things like that. Pretty much every type is a member of the EQ type class. And we'll see some examples. When we start doing user-defined types, we'll see some easy ways to make our types part of these kind of standard type classes. But that'll be later.
Quick question. Would then like so is there like a hierarchy of types then? Is EQ at the top and then it descends down to like chars and bools, or?
No. There are hierarchies between type classes. There are hierarchies between type classes, but not between types.
Okay, thank you.
So,
go ahead.
When it lists all the tuples that are instances of EQ, why does it only go up to a certain length? Is that just convenience? Or is that nice, like...
I think it's just it can't do all of them, so it does a handful of them. Yeah. This makes it kind of annoying because it's got all these tuples in there. Okay, so we'll keep going. So another example of a type class is what's called ord. And this basically stands for ordering. So it's types with ordering. So for example, like the less than, the greater than, min, max are all examples of operations for ord. Okay, again, we've got all these tuples, but we can ignore that. If we go up to the top, we can see class EQA. So actually, this is anything that's ord also is EQ. So that's what this first line is saying. This is basically like creating that hierarchy between type classes. So it's saying that ord is a subtype of EQ. So here, you can see the less than function, less than or equal function, greater than or equal, max, min, etc. Okay, so another very simple one, type class is called, show. And this has one function, which is the show function. And you can think of this kind of like toString in Java. So if I do, it's going to give me a lot of stuff again. Tell me about show. So the main function is the show function. So this basically takes a value and then displays it as a string. So as an example, I can say show the value 1. So 1 is an int. An int implements the show type class. And so then if I say show 1, it basically turns 1 into a string and displays it. There's the reciprocal of show, which is read. And this has the read function, which basically takes a string value and converts it into its value. If I say read 1, oh, whoops. I have to, so the problem here is that the string, I have to specify what I want the type to be of the result of read, because 1 is just a number, right? So I have to give a specific type. So the way I would do this is I would say read, the result of read 1 needs, oh, it did the typing sound. Okay, whatever. So I need to specify what I want this result to be. So in this case, I say the result of read 1 should be an int. I can do the same thing with an integer. I can also say I want it to be treated like a double. Okay, but if I wanted it to be like a bool, I get a problem. Okay, any questions about that? Okay, and then another just common one is enum. And this is for sequentially ordered types. So this is what allows us to do the enumerations, list enumerations. So the two functions that are, the two main functions in enum, if I come over here, so I can ask for info on enum. So the two main functions are, you can see them here, there's SUCC and PRED, so successor and predecessor. So the basic idea is the successor is like the next value in the sequence, and the predecessor is the previous value in the sequence. So the successor of 1 is going to be what? Anybody?
2.
2, okay. The predecessor of 2 is going to be 1. The successor of A is B. The predecessor of Z is Y. Okay, because char implements the enum type class. So we can actually ask for information about char, and we can see what all the type classes char implements. So here we can see on the second line, char is a member of the enum type class. It's also a member of the EQ type class. It's a member of the ord type class, of read and show. And just what that means is that all those functions we can call on characters.
Real quick, is the character based on ASCII values?
Unicode, but similar. Yeah.
Numcode?
Yeah, they're Unicode values, yeah, which is basically the same, but there's more of them. Unicode is the same thing as ASCII. There's just like way more Unicode characters than ASCII characters. So it's the same idea.
It says that the empty tuple is part of enum.
Yeah, I think that's, yeah, I'm not sure what that actually means. That's good. So does this mean I can do this? Whoops, I can't do that. Okay, so yeah, there's only one of them. So the successor of that, oh, whoops. Oh, what's going on here? Oh, that's spelled it wrong. I'm not sure. Oh, that's an exception. So there is no success. Yeah, I don't know. It's kind of weird. Basically, it's saying that it doesn't have a successor. It doesn't have a predecessor. There is no predecessor. It's throwing an exception. It's like a runtime exception. So it's just some weird thing. I don't know, probably to make it uniform with tuples, because enum does, I guess, support the ability to enumerate through tuples. Okay, we'll skip that for now. That's maybe more detail than we need. So the next type class that's important that we've seen a bunch already is the num type class. So basically all the number types are members of num, at least indirectly. And so the num type class supports just basic mathematical operations. So if I look at this, so it tells me that the num type supports plus, minus, times, negate, absolute value, and so on. And then a word, an integer, an int, float, double are the basic. There's other primitive types, but you have to load those in from other libraries, other modules. So the default module comes with word, integer, int, float, and double as the num types. Like plus, times, minus, etc. By the way, just like in MyPL, there is no negative sign, so like -8. Is that true? I thought there wasn't. 5 plus -1. Oh, that does work. So at one point there wasn't a negative sign, and so this is what negate was for. Okay, but now actually it looks like it works just fine.
Isn't it that there's ambiguity between partially applied minus and unary minus?
Yeah, I think that's probably the problem. Also, you can't do, there is some precedence issues, so there's still some issues here. Okay, so just moving on, there's something else called an integral type class. This is probably rarer. But this is for whole number types. Which supports sort of different operations than you would for like floating point. So in particular, so like the mod or the quotient or remainder or like an integer division are only supported for the integral type classes. So this would be int and integer. So if I ask for the information about the integral class, it gives me like the remainder, modulus, and so on. So there's a bunch of other type classes for what we would think of as like floating point values or decimal values. And so I'm not going to go into those. We're not going to be using them much, but they are also part of the language. So one example is fractional, which is kind of the base of those. So, and if you want to know more about them, you can do info on fractional. Whoop. Yeah. Okay. But there's others. So another one is real. So it has yet more functions. And then actually, if I go back to fractional, you can see that fractional is a subclass of num. Just like integral is also, also subclass, well, it's a subclass of real and enum. Real is a subclass of num. So indirectly, it's a subclass of num. Okay, so again, I think these ones you should know. You don't need to memorize what the functions are necessarily. You should have a sense for kind of what the functions are, but you'll see these a bunch, especially like EQ, ORD, enum, num, integral, maybe fractional. So you should have a sense for what these are, kind of what they provide, and we'll see these in a few places. So the other thing is this is also part of Haskell's kind of ability to do type inference. So for example, if it sees that you're using equal operator, then it knows that those values have to be part of the EQ type class. And so to figure out what the types of those things are, it also knows what types are instances of the EQ type class. So it's all kind of tied into type inference in Haskell. Okay, so now just going back, to where we started. So this type, the type, of 42 is that. And so what this expression is here is what's called a class constraint. Actually, let me go back. This is the type of 42. This part is the constraint. So here, I would say 42 is any type, okay, such that the type is a member of the num type class. So that's this notion of a type constraint. So I'm saying 42 can be of many different types, and any particular one I'm calling A, and so long as, so 42 can be of different types so long as that type is a member of the number type class. In other words, so long as it supports all the normal arithmetic operations. Are there any questions about that? So it turns out that that Haskell has this very general kind of allows for very general kinds of types. So as another example of a type variable, so type variables don't have to be constrained. They don't have to be part of a type constraint. Just as an example, so if I come over back to Haskell, if I want to know what the type of the empty list is, so it gives me, that might be confusing. Let me write it out. It gives me this type list of T, okay? So the type of the empty list is a list of T. So what is this lowercase t thing? Somebody tell me, what do we mean, what does it mean when it puts lowercase t? Or we could replace that with a, like a lowercase a. Lowercase a, lowercase t, they're kind of the same thing. What is it?
It's just like a generic type.
Right. Well, yes. Specifically, this lowercase t, so here t is a type variable. A type variable, like I said earlier, ranges over, it's a variable that ranges over types. Just like int x, x is a variable that ranges over integer values. When I say this is a type variable, I mean that it's a variable that ranges over actual types. So for example, t could be int, or t could be integer, or t could be double, or t could be char. So all of the basic types, the type of this list can be, any type can be substituted in for t in this case. So what is this whole thing saying, given that?
Is it saying that it can be a list of anything? Of any type?
Yeah, well, it can be a list of any type. It can be a list of any type. So it's basically depends on the context where we're using the list, the empty list. So for example, if I have the value, if I take the letter A and I cons it with the empty list, for cons to work, the left-hand side and the right-hand side have to type check. Right? For this expression to work, the left-hand side and the right-hand side have to type check, and in particular, this right-hand side has a type, and the left-hand side has to be a list over those types. So for example, I can say A cons the list with the character B in it, this type checks. But I cannot say A cons the list with the value true in it, because this list is not a list of char, right? And I'm trying to add a char to it. So this is bad, this one's okay, and this one's okay too, but in order to get it to kind of work, we have to pretend like this is a list of char, which is exactly what we're saying in the type, is that an empty list can be a list of any type. Okay, so that's an example where we have a type, for the list here, we have a type that involves a type variable, but does not have a constraint. Whereas when we're talking about like the number 42, we also have a type variable as part of the type, but in this case, the type variable is constrained to be within this type class. So are there any questions about that? None? Okay. Everyone's good and understands all this?
So then, like, if you did A cons empty list has type int, it'd be an error.
Yes. So if I come over here, you say like this. Let me put it in parens. So that whole thing, you mean, has type int?
Well, list of ints.
List of ints. Right. So so this is somewhat complicated. So on the left-hand side of the colon, which has type, we're saying that we're basically creating a list with a character A in it. And then on the right-hand side, we're saying that that list has the type list of int. So this is like a declaration or an assertion that we're making, and Haskell's going to tell us you're nuts. No, this is false. And that's basically what it does. It says that we can't make a char and int, because those are two different fundamental types, basic types. Okay, so let's move on. We're going to move on to talk about function types. So that's kind of one of the last big things we need to know as we go forward here. So there's a function in Haskell for defined for Boolean values, which is called not. So I can say not true, okay, and it returns what we would expect. Or I can say not false. I can also say like not 1 equals 2. That's true. Okay, so not is just kind of just a very simple function. So then for functions, Haskell can also, so just like with values, Haskell can also tell me the types of functions. So I can ask for the type of the not function, and it gives me this weird thing. So I'm going to just explain a little bit about what this is. So first of all, I'm going to write it down. So not is a function that takes as a first argument a bool, and then we have this arrow thing, and then what not returns is a bool. Okay, so the arrow is usually read as 2. So for example, the way I would say this is not has the type. So again, the colon, you say has type. So I would say not has the type bool to bool, which sounds a little funny at first. So you can also think of the arrow as returns. Although this will get a little funny as we keep going. So if you feel uncomfortable saying 2, for now you can say not has the type, or sorry, using this kind of model of returns, we'd say the type of not, not takes a bool and returns a bool, okay, versus not has the type bool to bool, almost like a mapping. So not maps bools to bools. So again, the two ways to talk about this type, at least for now, the standard way would be to say not has type bool to bool. The kind of non-standard way would be to say not takes a bool and returns a bool. Okay, so let me give you another, maybe a little bit more complicated example. So again, there's this successor function. So I can say like the successor of 6 or the successor of A, for example. So we want to know what the type of successor is. So first of all, how many arguments does successor have? Somebody tell me. It should be easy.
1.
1. Okay. It takes the value 6, or takes the character A, or whatever. How many? What? Well, every Haskell function except for kind of a constant. Well, even a constant. Sorry. Every Haskell function returns a value, right? Because everything evaluates to a value. Everything is an expression. And so in this case, it would have there's one thing that it returns. Does anybody have a guess what the type of the thing that successor takes and returns is? So I'm going to write something like this is the argument and it returns something else. What do you think successor takes as an argument and returns?
Is it an enum? Does it have to do with an enum for the type class?
That's right. That's right, because successor is actually defined on the enum class. And so what it takes as values have to be values that conform to the enum type class. Okay, so so in this particular example, we're going to have to use type variables. Okay, because there's lots of different types that support enum or that are members or instances of enum. So in this case, successor will say takes an A, returns an A, but there's a type constraint, which is that A has to be, sorry, I ran out of room, an enum type. Should I clean that up? I have to say, this is the only, oh, I don't know if I can rotate it. Yeah. Oh, it's not big enough. This is the one thing this is the only thing that makes this a little bit nicer than a whiteboard. I wish I could do this on a whiteboard. That would be so awesome. I think you can do this with like maybe smart boards. I don't know. Okay, so I would assert that this is going to be the type of successor. So successor goes from A to A such that A is an enum type. So let's try it and see. That's what it is. By the way, it doesn't matter this type, enum A to A, the A doesn't really matter. It just has to be a type variable. So this is, whoops. These are equivalent. These two are equivalent. What about this? Are these three equivalent types, or are they different? This is a T.
The enum T to T to T one it is because the variable doesn't really matter. But the last one isn't because it's A, then T. So you're changing up the variable.
So exactly. So the variable name doesn't matter, right? But the pattern does. So for the first two, we have functions whose input and output. Sorry, let me do this. The input and the output have. What this is saying is that the input and the output type are identical because they're both of type A, right? So it's like saying int x equals 5, int y equals 5. It might be that x and y have the same value, or because they're two different variables, they might have a different value. And here, because I'm using A both on the left and the right-hand side of the arrow, I'm saying whatever type gets like bound to A, that has to be, if it's the input type that gets bound to A, the output type has to be that type. They have to be the same type on the input and the output. Okay, so this pattern, says the same exact thing. So the input and the output types have to be the same, and they have to be an enum type. But this one's actually saying something different. So here we're saying the input type has to be an enum type, but the output type could be anything. And they don't have to be the same. And so this is a very fundamentally different type. This is also, we'll talk about this a little bit more later. This is kind of a weird type. And this actually gives us some information about what the possibilities are that the function actually does. It actually limits what the function can do in this case. So we'll talk about that later. Okay, so I have another example. Last time we talked about some list functions, and one of the primary ones we talked about was the head function. So as an example, if I have a list like 1 to 4, I can call head on the list. What is it going to return?
Should return 1.
1. Okay, it returns the first element in the list. Okay, so now we want to figure out what is the type of the head function. Okay, so head, well, how many arguments? One. Okay, so it takes one argument, and then it's going to return something. Okay, what kind of a thing is the argument?
List of T's.
It's a list. Okay, and exactly, head doesn't like discriminate what types of things are in the list. It could care less, right? It just takes the first one. It doesn't have to be of any particular type. So then what gets returned? What's the return type? So if I give it a list of values of type T, what is it going to return?
T.
Right, it's going to return a value of type T. And so the return type is T. And there's no type constraint. Head can take any type list, it doesn't matter. And so if I come back over here, we can verify this. Oh, it used A instead of T, doesn't matter. So the head function takes a list of A and returns an A. Or in other words, head has type list of T to T. Okay, there's another kind of interesting function in for lists, which is called take. Okay, so if I come over here, whoa, sorry, getting wild. An example is, so basically what take does, is you give it the number of elements you want to output from the front of the list. So you want to take the first n values out of the list. So for example, if I have something like this, I'm saying I want to take the first 4 values from the list that I've genned up on the right-hand side. Okay, so what's going to return are the first 4 values. Like we talked about last time, Haskell is kind of unique in that we can pass in infinite data structures. So here, this is the list of all the positive ints, and so I can actually take the first 4 of those, or I can take the first 10 of them, etc. Okay, so so what we want is we want to know what is the type of take. So how many arguments does take have?
1.
2? Yeah, 2.
Has 2, right? It takes n, the number of elements that we're going to output, and then it takes a list. So it actually has 2 inputs and then 1 output. Okay, so what's the second input to take? What's the type? Again, it's totally generic, so I can take the first 3 letters from C to Z, right? So what's the second argument of take? What's its type?
List of T again.
Yep, so list of T. What does it return?
A list of T.
A list of T. Okay, and then the first argument has to be an integer value, right? It has to be an integer value. It turns out that take, I'll just tell you, the first argument is an int. Okay, and basically what that means is it's kind of like a choice that we're not going to allow you to take a large number of elements from a list. We're going to constrain it just to be of size int, which still is pretty big, right? Okay, So if I ask for the type of take, I guess the question here is what goes here? Like how do we specify multiple parameters? Okay, so I'm going to show you. Again, here we're using T and then Haskell uses A, it doesn't matter. So, oh, it's an arrow. It's just an arrow. What a surprise. And so this is a little bit different. So for now, actually this is kind of a tie-in to lambda calculus. So what we just saw was a tie-in back to lambda calculus. Okay, but I'm gonna try to explain what's going on. So the first thing is, before we go crazy, the one way to think about this is you basically look to the last arrow, and what's on the right-hand side of the last arrow is the return. This is the return type. I'm going to erase that. Okay, so one way to look at this is that, okay, there's all these arrows, but if you go to the last arrow, what's on the right-hand side, that's the return type. And then everything before it, these things are the input types. This is kind of like a traditional view of a function, right? A function is defined such that it has a list of input types and then an output type. So in this case, we would say the return type is a list of T, and the input types are, it's an int followed by a list of T, or something like that. Okay, but what's really happening is that an arrow is kind of a special thing, and an arrow always denotes a function. Okay, so the basic idea, and there's two arrows here. So the basic idea is that an arrow takes an argument it's a little hard to type or to write. So it takes an arg of the type on the right or on the left of the arrow. Sorry. So the first part is it takes an argument of the type on the left-hand side. So if we're just looking at this arrow, so the first arrow takes an int, because that's the type on the left-hand side, and then everything on the right of the arrow is what gets returned. So it returns the type on the right-hand side. Okay, so in our case, so this is so if we're looking at the first arrow, the first arrow specifies a function that takes an int, and then it returns the type on the right-hand side, which happens to be a list of T to T. So what kind of a thing is that? List of T to T. List of T. What kind of a thing is that? It's a function. So in other words, we can say something like take 4, where I fill in the first parameter. That corresponds to the int. This whole thing actually returns a function that has the type list of T to list of T. Okay, so if I kind of follow this notion of the arrow, the definition of the arrow, then if I just write take 4, what I'm saying is that this whole thing basically returns a function that takes a list, that maps a list of t to a list of t. Okay, this should be very much sound like lambda calculus, right? So in particular, like takes a value and then returns another function. Okay, and it's actually the same idea. This is what's going on here. So the key thing about the arrow operator, or the arrow, is that it's right associative. So the arrow is right associative. So for example, if I have a type like A to A to A, that's equivalent to A to, in parentheses, A to A. And the reason for that is because we read the arrows from left to right. Any questions about that? Okay, I'm going to skip over this, but in the lecture notes, there's a few exercises. So I ask you, and this I'll just let you do this on your own, and then you can check it in the interpreter. So you can use this as a way to help study, or just to make sure you understand the concept. So I ask you, what's the type of the tail function? What's the type of the null function? What's the type of list concatenation? And what's the type of list construction or cons? So you really need to have it should come very naturally to say what the type is for those things. Those are great, like quiz questions or whatever. Okay, so just going back to this notion of take 4, in this case, what's happening here is it's just like with lambda calculus. So we can kind of like partially apply functions and get back new functions. Okay, and when we do that, it's called partial function application. Again, just like in lambda calculus, the application part is basically the same idea. So I'll just kind of give you an example. So I can define a function. I'm going to call it take 4. And really, I'm just creating a binding, and the binding is to a partial function application. So I have the function take, and I just pass it in one argument, which is the int. So coming back on this side, basically all I've done is I've passed in the int. Okay, and that works fine. So now, if I ask for the type of my new function, take 4, what is it going to return? So again, over here, I just passed in this part. And so now, what should the type of take 4 be?
Does it only take in a list of type T or type A?
It's going to take in a list of type T, yeah. And then it's going to return a list of type T. Whoops. Type take is not a and. Okay. So again, it does exactly what we think it should do. So if I basically pass in 4 for the int, what I get back is now I'm getting back a function that takes a list of t and returns a list of t. And I can call the function. I can pass in more. I can pass in a list. So for example, I can get the first 4 elements from this list. Whoops, that's not gonna work. I can pass in a list, and it's going to return the first 4 elements of the list, just like it should. Okay, so again, this is very different than like a normal programming language, in the sense that I can't like pass one argument into a function that takes 3 arguments and then kind of use that somewhere else to fill in the rest of the arguments later. Like this is very different than most other languages, and the way that it's working is exactly the same way that lambda calculus works. Are there any? I'm going to move on. Are there any questions about this? Okay, great. So in the lecture notes, again, there's some more exercises that you can do kind of offline, just as a way to check your understanding. So, and they have to do with partial functions. So, and then kind of a couple new functions that I didn't talk about. So one is, or sorry, there's just one additional function called replicate. And so replicate's kind of similar to take. It has a similar feel to it a little bit. But I give some partial function calls, and then I ask you for what the types are. Again, those make for good kind of quiz questions. And then again, with the exercises, you can try to do the exercise, and then you can test yourself just in GHC in the interpreter. You can also, in Haskell, do lambda functions directly. So Haskell supports lambda functions directly. In other words, unnamed functions. And basically the way this works, it's the syntax, like I said, you could use on the quiz for the most part. So basically, instead of saying something like lambda x dot lambda y dot x, let's say, in Haskell, you just use a backslash, use a parenthesis and then a backslash, and then you give the argument name, and then instead of the dot, which means something else in Haskell, you can use a single arrow. So as an example, I can write something like x times x. So this would be a lambda function that squares the x. As another, or I can actually show this. So I can do like let square equal lambda x to x times x, and then I can call square of 3, for example. I can also just do it on the fly. So I could say like lambda x to x times x, and then give it the value 3, and it'll just calculate it right there. One of the reasons why Haskell supports lambda functions is this idea of higher order functions, which we talked about in the very beginning, that you can pass functions around to other functions. So a good example of this is filter. So filter takes what's called a predicate, which basically just is a function that returns true or false, and then takes a list, and essentially it iterates through the list and takes each element, plugs it into the predicate. If the predicate returns true, then the element goes into an output list. So for example, if I want to make sure that given a list, I just want to select the values in the list that are less than 5, then one way I can do that in just one easy statement is I call filter, which is built in. I pass it a lambda function that basically just takes a value and returns true if that value is less than 5, and then I pass it the list. And so this is going to return a list with all the values in the original list that are less than 5. So that's, I'm not going to go into a lot of detail right now about this, but we'll see this later when we start talking more about higher order functions, that they're very convenient to call higher order functions to do work, more complicated tasks, and we can use lambda functions to just create these very simple functions, pass them into the higher order functions instead of having to always be creating like new functions to do really simple things. Okay, so I'm gonna, I wanted to just real quick, with the time we have left, which is just a few minutes, to run through a few more list functions that you need for the homework assignment. So in particular, I'm going to talk about length. Then I'm going to talk about this function called init. I'm going to talk about last, which you don't need for the homework assignment, but just to give you a sense, there's something similar that you're doing in the homework assignment, and then reverse. We already talked about take. The last one is what's called drop. So length is pretty easy. Length basically just returns the length of a list. So if I have a 100 element list, length is going to return 100. Okay. Actually, I'll jump around a little bit. So reverse just reverses a list. Okay, that one's pretty simple. So drop is similar to take, except instead of taking the first n elements from a list, it does not include the first